Today we are going to go over stellar evolution. Our objective for the day is to list and describe the stages in the evolution of a star. So we are going to go over how a star evolves over time. And we're going to go over the stages as well. So we're going to start with birth. Stars are born in an interstellar clump of matter full of dust and gases called nebulae. Nebula is singular. Okay, so it's a nebulae. Clouds cool and condense enough for hydrogen atoms to join together into hydrogen molecules. In the Milky Way, clouds are approximately 92% hydrogen, 7% helium, and 1% other molecules and elements such as carbon monoxide. In nebulae, particles are widely dispersed despite having hundreds of times the amount of mass. Dense areas of the nebulae attract more particles over time until a gravitational field can be formed. The cloud begins to collapse on itself by immense pressure. A furnace ignites and a star, a ball of hot gases, is born. The life cycle becomes a balance of gravity trying to shrink the star and put out the furnace, but the thermal nuclear energy is trying to expand it and make it grow. So, just like with humans, it starts with birth. Now, we have protostar stage. Gravitational energy converts to thermal energy. Thermal means heat. So we have energy from gravity that's going to be converted into heat energy. So when it converts to heat energy, there's obviously going to be an increase in temperature. Red light, which we determined had long wavelengths from energy, but it is not hot enough to engage in fusion. So in the last video, we had nuclear fusion where we were taking elements and we were combining them together in order to make other elements. Okay, we were fusing elements together in order to change what kind of elements that were present. There's not going to be enough heat for that to happen at this stage. Gravity picks up its pace and it heats up internally. At about 10 million Kelvin, the heat and pressure is so intense that 4 hydrogen nuclei fuse together to form helium. This is called hydrogen fusion. I'll move over here now. Our main sequence stage. Heat and motion from the protostar create an outward force. Remember, heated gas expands. Once there is a balance between gravity and gas pressure, you have a stable star. Minimal changes in size or energy output will happen with a main sequence stage, or during the main sequence stage. And 2 types of main sequence. We have hot, high mass blue star, which burns through its hydrogen fuel fast, as in a few million years. Crazy to think that a few million years is considered to be fast, but that for the life of a star, a few million years is that's a very short lifespan. Our smallest, which will be our red stars, take hundreds of billions of years to burn through because they are not burning very fast. They are not burning through all of their fuel at a very quick rate. So they have lots of fuel for hundreds of billions of years. And a yellow star, which is an intermediate kind of a mass, burns through in approximately 10 billion years. Our sun is a yellow star. It's only about 5 billion years old, so we still have half of the life of our star left. And this is where stars are going to spend a majority of their life. About 90% of their life is going to be spent during this main sequence stage. Then we have our red giant stage. This is when our hydrogen fuel is depleted, leaving behind a helium core. There's no more fuel, so gravity is going to collapse the star in. Collapsing creates thermal energy, which then heats the hydrogen-rich shell and bloats and burns even faster. Main sequence, or red giant, intermediate mass stars. About 1 billion years to become a red giant, and then it's about 100 times larger. Main sequence supergiant. Supergiants referred to high mass are about 1,000 times larger. And red, due to large surface area, means that it is fast cooling. Temps reach 100 million Kelvin in the core, causing 3 helium nuclei to make a carbon nucleus. Hydrogen and helium are consumed for energy, and even heavier elements than carbon are made, such as iron. Oh, let me finish on you real quick. I apologize. Once the core becomes all iron, or oxygen, magnesium, silicon, and carbon, the core can no longer create energy. That is because it has become a metal, well, and a few non-metals, but iron, magnesium, both those are metals. And we have burnout and death. Low mass stars, red dwarfs, are most common in the universe, and they remain stable for at least 100 billion years and longer. They never become hot enough to ignite helium, and no bloating. They just shrink into hot, dense, white dwarfs. Okay, so they're just going to continue to shrink. They'll continue to get smaller and smaller and smaller. That's just what they do. And then we have intermediate mass stars, which is our sun. Our sun will go through this kind of process in a few billion years. They blow off their bloated atmospheres within expanding clouds of gas. They become tiny white dwarfs in the center of the planetary nebula. And then high mass stars, because of their short lifespan, they will explode into a supernova. A supernova is full of gas and debris, and our stars become millions of times brighter due to this. Now, here's a video on this down here so you guys can see the link up at the top. Here's a video on the evolutionary stages of a star. Make sure that you watch that. It's going to help you. It's a supplemental kind of a video to help you guys. That way then you hear someone else's voice that is not just mine all the time. Hopefully it'll help some of you guys that might be struggling with this. Hopefully it'll help you learn this just a little bit better. Hold on. Why is it not moving? Now, let's move this over here now. Here's our star cycle diagram. Okay. Notice how there are 3 prongs because we have 3 different kinds of stars. We have low mass, intermediate mass, and high mass. Okay. So we have 3 prongs to this kind of fork coming off as soon as it becomes a protostar. So all stars begin as a molecular cloud. Stars are born from clouds of cold gas and dust. And we have our protostar. This is where it'll kind of determine if it's a low mass star, if it's an intermediate mass, or if it's a high mass. It'll be at this stage right here because protostar, the collapse of a cloud converts gravitational to thermal energy, creating a dense glowing protostar. If it collapses on top of itself and a lot of thermal energy is created, it's going to become one of these 2, intermediate mass or high mass. If it doesn't create a whole lot of thermal energy, but it collapses on itself and becomes really small, then it'll become a main stage, or not a main stage, a low mass star in its main sequence. Now remember, main sequence is where our star is going to spend a majority of its life, about 90%. So a low mass star during main sequence, the star is dim and red and it fuses hydrogen in the core. Now, a low mass star is never going to fuse helium or form a red giant. It's just going to become a white dwarf. So it's going to live out its life and then just become a white dwarf. It'll become a white dwarf after running out of hydrogen fuel. The stars slowly cool. Intermediate mass stars, this is what our sun will go through, will be this right here. It's starting with our main sequence. It's going to be yellow-white, and it's going to fuse hydrogen in its core. It will become a red giant. Fusion in a shell around the core causes the star to expand. In the first red giant phase, hydrogen fuses in a shell around a helium core. In the second red giant phase, hydrogen and helium fuse in shells around a carbon core. After its red giant stages finish, it will become a planetary nebula. The nuclear burning ceases. Light from the hot stellar core causes the expelled envelope to glow. That's what this is right here on the very outside, this kind of pretty part of it. And then it will become a white dwarf. If you see, the white dwarf is already right here in the middle, but there is a planetary nebula around it. As soon as the planetary nebula ceases to exist, it will turn into a white dwarf. Yeah. That's what intermediate mass star is going to do. Then we have a high mass star. These are going to be blue and white and very luminous, and they're going to burn very, very, very quickly. Okay, when this happens, they're going to become a supergiant. Fusion in a shell around the core causes the star to expand. In the first red giant phase, hydrogen fuses in a shell around a helium core. In the second red giant phase, hydrogen, helium, and other elements fuse in shells, ultimately forming an iron core. And then we have a supernova. The energy released by the collapse of the iron core causes the star to explode. When the star explodes, it's going to become one of two things: a neutron star or a black hole. A neutron star is the core collapses to form a dense, city sized object composed of neutrons. In our black hole, in stars larger than about 25 solar masses, the iron core collapses to form an infinitely dense black hole. We'll go over black holes later. We're not going to go over them today. Once again, they're kind of a confusing topic, kind of like dark matter and dark energy. Um, so we'll go over that later. But you do need to know the difference between these three types of stars: low mass star, intermediate mass, and high mass, and what their life cycle is based off of each one. That is all that I have for you guys today. Next video, we're going to go over stellar remnants. Remember that you can always join the class in person. I perform these lessons live in the Microsoft Teams meetings, so you guys can always join those instead of watching the videos if you find it to be more helpful to be there to ask me questions as I go through it. Make sure that you do your warm up. Make sure you do your DOL. Remember, your DOL is how I take attendance, so you should probably go do that DOL right about now. That's all I got for you guys today, though. Please do your homework. Please do what you guys need to do. Get your grades up, and I'll see you guys next time.